let's now go through the math for estimating and predicting azeotropes. Okay? And so we know that the criteria for the formation of an azeotrope are the following two things. First of all, the liquid and the vapor mole fractions for a species have to be equal. And then also, we need to have an extremum of, if we're looking at the PXY diagram, we have to see an extreme in the pressure. So that means is that the partial derivative of pressure with respect to xi at a constant temperature, that partial derivative is going to be equal to 0. For our modeling purposes, we're going to look at the same type of system that we've been looking at previously. So namely, we're going to assume that the vapor phase is an ideal gas mixture. And our liquid phase, that's where the non-idealities are going to occur. So we will have a non-ideal solution. Okay? All right, and so for the vapor-liquid equilibrium, we could once again go to the modified form of Raoult's law, where our partial pressure, which is equal to yi times total P, is equal to xi times gamma I times pi sat. But we know that if we have an azeotrope, xi is going to be equal to yi. And since they're on both sides of the equation, we could cancel them out. Therefore, we could rearrange the equation so that our total P is just equal to gamma I times pi sat. Or if we rearrange it, what we could say is that gamma 1 in our binary mixture is equal to P over P1 sat, and gamma 2 is equal to P over P2 sat. Okay? All right, and so, this already we've gained some insight into the system, such that at the azeotrope, we know that the activity coefficients are just going to be equal to the ratio of the total pressure over the partial pressures. All right? But if we want to gain more insight, namely, we want to figure out at what x1 or x2 values the azeotrope occurs, what we're going to do is we're going to need to assume some sort of functional form for our activity coefficients. Okay, so we will now need some sort of mathematical model for gamma I. Okay. All right, and so for this example, let's start with just a very simple model for gamma I. We're going to use the one parameter Margulies equation. Okay. All right, and so in the one parameter Margulies equation, if you remember, it's just equal to A times x1 times x2. Or we could rewrite this in terms of only x1, or if you wanted, you could do it only in terms of x2. All right, now if we go through the act of, we know that the activity coefficients are going to be related to the partial molar excess Gibbs energy. And so if we go through that calculation, we get that the ln of gamma 1 is equal to a x2 squared, and the natural log of gamma 2 is equal to a x1 squared. And so there's a sort of symmetry that goes on here with the one parameter Margulies equation. We could also just solve these explicitly for gamma 1 and gamma 2. All right. And so now that we have equations for gamma 1 and gamma 2, we could go back and we could plug them in to the pressure equation. Okay. So we know that total P is just equal to P1 plus P2. And if we plug in both the modified form of Raoult's law and the result we got from the Margulies equation, we get this. Okay. All right. And so, we have this now somewhat kind of long equation. And if we knew a pressure value, if we were given a total pressure, perhaps we could go out and solve for, an x1 value or an x2 value that would correspond to the azeotrope. But we could do one better. We could actually keep going through this analysis without defining a total pressure by invoking the second criterion for the azeotrope, which is the fact that the azeotrope occurs when this partial derivative is equal to 0. Okay? And so at dp dx1, constant temperature, we know that that derivative, when it's 0, we have an azeotrope. Okay? And so what we'll do is we're going to take the derivative of equation 1, and when we take the derivative, we're going to subject it to the following constraints, which is that the sum of our mole fractions needs to equal 1, and consequently, the derivative of the mole fractions have to equal 0. Okay? All right. And so if we go out and take that partial derivative, see if I have enough room. We'll get this equation. So P1 sat exponential a x2 squared plus 2 a x2 x1 times negative 1 P1 sat exponential of a x2 squared. And that negative 1, it just comes from the fact that I took the derivative of x2 with respect to x1. And so based on this constraint, we know that those are negatives of one another. Okay, so that's just a small detail. Exponential of ax1 squared plus, I'm going to go to a new line, 2a x1 x2 p2 sat exponential of a x1 squared, and this entire derivative is just equal to 0. Okay? So we have a fairly long equation, right? And it's not clear, what we learned so far. But if we go through some algebra, we could actually simplify the equation like this, into this form, where P1 sat exponential of a x2 squared plus P2 sat a x1 squared, close brackets. Oh, there should be, this is the exponential of this. Okay. And then we have another bracket, which is just 1 minus 2a x1 x2. Okay. All right, and so now we have the equation in this form. And so essentially what this is saying is that in order for this thing to always be true, both the stuff inside this bracket and the stuff inside this bracket, both of those things need to be equal to 0. So essentially for equation to be satisfied, we find that we have two roots. Okay. All right, so we have two roots in this equation. And so to get more insight into what this equation is telling us, let's look at each of the brackets independently. So let's first look at the bracket here on the left. So we get that P1 sat exponential of ax2 squared plus P2 sat exponential of ax1 squared, that has to be equal to 0. We could rearrange this equation so that we have x2 squared minus x1 squared, or if we wrote this only in terms of x1, we would have a 1 minus x1 squared minus x1 squared. In any case, this would be equal to the natural log of the ratio between the two vapor pressures. Okay? All right, and so what we get is that if we want to find the azeotrope composition x1, or the composition or the mole fraction in which the azeotrope occurs, all we would have to do is start with this equation, which is independent of any total pressure, and we would just need to solve for x1. The thing I want to remind you is that the two vapor pressures here, these are both a function of temperature, and this Margulies parameter here, this is also a function of temperature. So as we change the temperature of our system, it's going to change these values, and as a result, it's also going to change the x1 that satisfies this equation. Okay? And so, really, if we solve for this, what we get is that x1 azeotrope is just equal to, if I call this ratio here beta, which is a function of temperature, our azeotrope composition would just be 1 minus beta divided by A over 2. Okay? And so what we find is that one could just find, regardless of what the total pressure in your system is, one can just find that azeotrope composition very quickly. But we have to remember that in order to do this analysis, we assumed that our excess Gibbs energy could be described by a one-parameter Margulies equation. Okay? And so this result is only valid for the one-parameter Margulies model. Okay? All right, and so that's, if you're dealing with a one-parameter Margulies equation, this is the shortcut equation that would give you that azeotrope composition. Okay. All right, so we looked at the left bracket in our equation. Let's now look at what information that right bracket is going to tell us. So for the right bracket, we have 1 minus 2a x1 x2, or if we could rewrite it just in terms of x1. We have that this is equal to 0. Okay. We could rearrange this equation so we have it in this form. 2a x1 plus 1 is equal to 0. Okay. And essentially what we get is a quadratic equation where if we solved it out, the solution of the equation would correspond not necessarily to the azeotrope formation, but it would correspond to the case where we would have liquid-liquid phase separation in the mixture. Okay? And the reason for that, I'll actually talk about in later videos, okay, about why this represents liquid-liquid phase separation rather than an azeotrope. I'll talk about that more later. But essentially what we could do is we could rearrange this equation to give us a value where we say A is equal to 1 over 2x1, 1 minus x1. Okay. And so what this tells us is that for a given x1 value, we could find an A value that triggers liquid-liquid phase separation in our system. Okay. And for now, I'll just say that the next series of videos will focus exclusively on this. Okay. But in order for, just to give you an idea of how this equation would work, if we plugged in a mole fraction of 0.5, we would find that this sort of critical A value would be 2. And so if our A value has a magnitude of 2 or greater, then we would have liquid-liquid phase separation in our system.